Hello friends, after learning the basic descriptive statistics and some techniques of simple regression and multiple regression, we are now actually going to delve into the core course of statistics, namely statistical inference. Statistical inference and probability theory are the two main core subjects of theoretical statistics, of which we are going to consider some of the techniques from statistical inference. We will not be considering the theory of probability in this module, as mainly you people will be working on the data analysis and arriving at the conclusions after analyzing the clinical trial data. There will be a very less chance of you people being involved in computation of probabilities and the related stuff. That is why we have not included the theory of probability in this module. Coming to today's agenda, we will try to understand why we need statistical inference and what is statistical inference. Then there are certain terminologies like parameter, statistic, sampling distribution of statistic, what we understand by the estimation of parameters, population and sample, point estimate, similarly interval estimation, the difference between the two, point estimation and interval estimation, and the confidence interval, which is nothing but the interval estimation. So let us proceed and enjoy the core subject of statistical inference. In statistical data analysis, it could be any walk of life, any field of real life situation where you are collecting data, classifying it, summarizing it and analyzing it. So the third step of statistics is analysis of data, and then final step is interpretation and conclusions. That is how the subject statistics is defined. So we are currently into the analysis stage of the definition of the science of statistics. So we would like to infer from the data that we are available with. Means we may not be available with the complete data or the complete population, but we are available with a data on a sample which is a part of the population. So the statistical inference tries to deduce properties of an underlying distribution by analysis of data. Using the statistical inference techniques, a statistician tries to get the knowledge or tries to infer about the population on the basis of the sample, and that sample has to be a random sample in order to apply these statistical techniques. So inferential statistics enables us to make statements about a general population using the results of a random sample from that population. With statistical inference, there are many well-known statisticians' names associated. Some of them are Fisher. Fisher is called as the father of statistical inference. Pearson, Neyman, Lehman. So these are the great scientists, statisticians. They were not that time statisticians, they were scientists or mathematicians working in their respective fields. For example, Fisher was working in the agricultural data analysis and he worked on the design of statistical experiments. So basically, we want to infer about the population which is difficult to handle or the population parameter which is unknown, and we want to make certain statements about the value of the population parameter, that is called as hypothesis in statistical inference. So, we will slowly learn all these things which we cover in statistical inference. In order to apply the statistical inferential techniques, one has to have a random sample from the population. I remember that in one of our sessions I have talked about what is meant by random sample and what is the difference between a random sample and an arbitrary sample. So, random sample is not an arbitrary sample. Random means that while drawing that sample, you are giving an equal chance to every member of the population for being selected in the sample. So, if you ensure that of giving equal chance to every member in the population for getting selected in the sample, then you are drawing a random sample. So, there are then several methods of drawing random samples. That is a branch of statistics, sampling methods. We are again not going into the details of the same. If you look at statistical inference as a course, then it is first classified into two branches, parametric inference and non-parametric inference. Now, what are these things? When you have data, there are two ways to analyze that data. If you know the pattern in the data, and suppose you can come up with a model for that pattern in the data, we have talked about these statistical distributions are nothing but statistical models. So, if we say that so and so variable is coming from a normal distribution with mean mu equal to something and sigma equal to some number, then that means we are using normal distribution as a model for that data. So, if we are using some available distribution as a model to explain the behavior in the endpoint, then we are into the parametric statistical inference. Most of the times, there are typical models used in parametric statistical inference for the different types of endpoints. For continuous endpoints, we generally use the normal distribution. For some of the lifetime distributions, life of a person, life of an electronic component, we use the exponential distribution or gamma distribution. For the binary data, we use binomial distribution and so on and so forth. So, these are the different statistical models or statistical distributions on which we bank upon while doing the statistical analysis. So, if we are using these models, then we are using the parametric inference. If we are not sure, see, in order to use a model, proper model, at least there should be a match between the model and the behavior in the data. If we don't see that match, then it is very wrong to use any of these distributions as the model. Because if you choose a wrong model and base your analysis on that, then your conclusions or your inference will be totally wrong. So, when you are not sure about the underlying statistical distribution, then one cannot choose any of these parametric models. Then you are into the non-parametric branch or non-parametric setup, where you don't assume that the variable is following a normal distribution or gamma distribution. You just assume that the data is your world and you try to infer from the available data. So, that is the basic difference, fundamental difference between parametric and non-parametric statistical inference. There are various techniques in non-parametric inference, and SATEL's stat exact and log exact deal with this branch of statistical techniques, and further that to the exact statistical techniques from non-parametric inference, but that is beyond the scope of this module or this particular session. We will be considering only the parametric inference branch. So, in parametric inference, now as you know that the underlying statistical population is mimicked by the statistical distribution. So, the population now is nothing but the statistical distribution, or the statistical distribution plays the role of the parent population from which you are drawing the sample. So, once you are into the parametric setup, now you know that a statistical distribution model is characterized by some parameters, by a number of few parameters. So, for example, I might have told you this earlier that normal distribution gets identified by specifying the value of mu and standard deviation sigma. So, it is like telling the name and surname of a person so that the person gets identified. So, if we assume normal mu sigma as the population or as the statistical distribution from which you are taking the sample, or you are assuming that the sample is coming from the normal distribution, then the question comes about estimating these parameters. So, the theory of estimation talks about the estimation of the unknown parameters of the underlying statistical distribution. For example, what is the value of mu? What is the value of sigma? So, that question you are trying to answer with the help of your sample, that gets covered into the theory of estimation. Whereas, in testing of hypothesis, you make certain statements about the unknown parameters. For example, you may say that the average increase in the induced sleep by a sedative drug is say 5 hours. So, you are saying that mu is equal to 5 if you are assuming normal mu sigma square distribution. So, that is the claim that you will be making. So, these claims are nothing but the hypothesis in testing of hypothesis. Further, you would either want to accept that claim or you would like to ratify or reject that claim, that on the basis of your data. So, that is the testing of hypothesis. Further, the theory of estimation is branched into two: point estimation and interval estimation. We will talk about these details in due course of time. Let us first of all understand some terminologies. Parameter versus statistic. Parameter is a quantity that describes a characteristic about the population, so about the model. For example, when we talk about normal mu sigma square, then mu and sigma are called as parameters. Whereas a statistic is data that describes a characteristic about a sample, such as sample mean, sample median, sample variance. So, these are the functions of your data or your sample. So, the statistic does not involve any unknown quantity. Parameters are generally unknown. The very reason that the parameter value is unknown, we are considering a sample. If the parameters themselves would have been known to us, then there is no question of taking any sample and there is no question of doing any statistical inference. So, the parameter is like God, we don't know about, we try to find out how does the God look like. So I would say that if the God is something, and then you would like to say that a statistic is Ram or Krishna, something like that. So you are trying to estimate the value of the parameter on the basis of your sample. Some of these values or some of these estimators and parameters, proportion. In case of binomial or binary endpoint, we are generally interested in the proportion of patients cured or proportion of patients discharged or proportion of patients who develop tumor. So any such event, binary event, yes, no kind of thing. We have seen the different types of endpoints in our, I suppose, the first or second lecture. So that proportion, overall proportion, how much percentage gets cured by so and so drug. So that's what you are talking about, which is unknown, and then you would like to estimate it from the sample proportion. You cannot handle the entire population, and then you handle a sample, and from that sample you find out the number of successes and take the ratio. If suppose there are 100 patients and 30 of them show the positive result in which you are interested in, then 30 divided by 100, that is 0.3, becomes the sample proportion. So when you compute the sample proportion, you get some idea about the population proportion. So that you say that my sample proportion estimates the population proportion. So sample proportion is a statistic and the population proportion is a parameter. Value of the sample proportion for your sample is the estimate, and the sample proportion on a whole is known as an estimator. So there are finer and finer details about this. Let us not worry about. For us, the concept is important, and what we are trying to see from our sample, that is more important. So the parameter value mean mu, whereas sample mean is x bar. Median, there can be population median, there can be sample median also. So you can have sample median as an estimator, but there are other estimators also. Variance, sigma square. If the underlying model is normal mu sigma square, then variance parameter is sigma square. How would you estimate it? You will estimate it from the sample variance with divisor n minus 1 as s square. I suppose we have talked about this also, that what is this n minus 1 and n, all that. We will see again. Standard deviation, then there is no unbiased estimator or commonly used square root of variance estimator above. See, as I said, that parameter is the value, the single value for that which is unknown. We are trying to estimate it from the samples. Now what estimate should we choose? There can be several estimates. For example, if we are talking about the normal distribution mu as the model, then mu is the population mean. But mu is also population median, because mu becomes, for normal distribution, mean, median and mode, all of them coincide and they are equal to mu. So in order to estimate the value of mu, can't I choose sample median instead of sample mean? Because mu turns out to be median for the population also. So the answer is yes, you can choose. So median, sample median can also one of the estimators. Sample mode also can also be one of the estimators. Why? Suppose if I say that I will take a sample of 100 patients and I will say that the 10th patient value, the value of the 10th patient, observation on the 10th patient is my estimator. nobody is going to stop you on choosing that estimator. That is a proper estimator. You can, it is up to your will to decide which estimator you would like to choose. Or you can say that the first person's response I will consider as an estimator of mu. Or I can say that the first person's and 10th person's response divided by 2 as my estimator of mu. Or then I can say that let me remove the first 25% and the upper 25% in order to remove the outliers, take the middle 50% and then find their average, which is generally known as trimmed mean, etc. So that is my estimate for mu. So the point which I want to make here is that there can be hundreds and thousands of estimators which you can think of to estimate the value of mu, as there are 33 crores of gods to estimate the god. Similarly, there can be several, infinitely many. Now the question is, which one is proper? Which one should we go by? So then there are such concepts like unbiased estimator, consistent estimator, maximum likelihood estimator, and therefore the statistical inference course or statistical inference branch flourishes like anything. Before going into that, let us just pictorially understand what is happening here. This is a population of people, patients say, and then the parameter you are interested in is the average height of this population, okay, average height in the population, and then you would like to estimate it from the sample. So first you draw a random sample, you pick the people randomly, and then you compute the average height in the sample. So remember that you are computing the average height in the sample and that turns out to be 5 feet. You don't know the average height of the population, which is the value of the parameter. So the 5 feet value is the value of the statistic which is estimating the parameter. So that is the concept explained pictorially. Okay. So this was the point estimate. 5 feet was one of the point estimates. You had used the estimator as sample mean to estimate the population mean. So point estimation refers to the process of estimating a parameter from a probability distribution based on data observed from the distribution. In short, I would say that point estimation gives you a single value for the unknown parameter. So, just I was explaining that once we can think of several estimators, then there are different types of estimators like unbiased estimation, consistent estimator, maximum likelihood estimator, minimum variance unbiased estimator, minimum variance bound unbiased estimator, estimation by method of moments, and several others. Of all these theoretical estimations, I am just going to consider the unbiased estimator here because it is very easy to explain and most of the times that serves the purpose. So, unbiased estimator means the estimator for which the expectation equals the population parameter. So, the expectation of the estimator equals the population parameter. So, that estimator is called as unbiased estimator. Now, what is meant by expectation? You can think of expectation as mean or average. So, the arithmetic mean of the estimator equals the population mean and therefore that is known as unbiased estimator. So, let me go to my favorite Excel example in order to demonstrate the concept of unbiasedness. Here I have taken a very small population. This is my population of 5 units. The values are 2, 4, 5, 6 and 8. So, if you compute the mean of these, then the population mean is 5. Pretending that this is unknown and I want to take a sample of size 2. Suppose I take a sample of 2 and 4, first 2 units. Then I take a sample of 2 and 5, second sample. Then I take 2 and 6. So what am I doing? I am listing out all possible samples from this population of size 2. See, I am not writing, after writing 2, 4, I am not writing 4, 2 because the order is not important. Sample is a group of objects, not the ordered thing. So, I can list out all these samples. How many are they? Those who have learnt permutations and combinations can readily answer that since you are selecting 2, it is 5 choose 2 and 5 choose 2 in all 10. So, these are in all 10 samples. Okay, so it's 20. So, these are in all 10 samples. For these, each of these samples, I have computed the sample mean. So, this is sample mean. So, for example, for the sample 4 and 5, the sample mean is 4.5 because I am just adding and dividing by 2. For this 5 and 8, the sample mean is 6.5. So, this is sample mean. Now, one thing you will notice, and that is a very important observation, that as your sample changes, the sample mean also changes, right? Somewhere it could be the same, but overall it changes. So, as the sample changes, the value of the sample mean changes, obviously. Therefore, I can treat this sample mean as a variable. So, the statistic which I am talking about here, sample mean, as a statistic, as an estimator, that is a variable in statistical sense. So, if it is a variable, then you can talk about its mean, you can talk about its standard deviation, you can talk about its everything, whatever we can talk about any variable. So, the distribution of the sample mean is known as the sampling distribution. So, basically sampling distribution is nothing but the distribution of the test statistic. Statistical distribution of the test statistic. So, that is a very important and to be understood kind of statement. I would say that sampling distribution is nothing but the distribution of the test statistic. How it varies and what it shows, like that. If for example, suppose in place of these 5 units you were having 500 units, then you are taking the samples of 2, then there will be 500 C2, then it will be large number of large data, then you can plot its frequency distribution, histogram, etc., etc. So, that distribution will be known as the sampling distribution. And then here, if you take the mean of these sample means, see what am I doing? Mean of sample means, I have taken the mean of these numbers and that mean turns out to be equal to the population mean. It is not a magic, it is correct. So, this is the mean of means, mean of sample means is coinciding with the population mean. And this will happen not only for samples of size 2. If you take samples of size 3, if you take samples of size 4, but obviously the sample size should be the same throughout all the samples. So, if you list out all the samples of size 3 and do the same exercise, you will get the expected value of the sample mean as the same as the population mean. This is known as unbiasedness. Okay. So, expected value of the sample mean is the population mean or the mean of sample means is population mean. So mean of test statistic is the parameter, and therefore this particular test statistic, that is sample mean, is an unbiased estimator of population mean. So what have we understood? Sample mean is an unbiased estimator of population mean. Okay, and the distribution of the sample mean is the sampling, called as the sampling distribution of the sample mean. Once you have a distribution, just as you have talked about the mean of the distribution, similarly you can think of the standard deviation of the distribution. So standard deviation of the distribution of sample means will be nothing but the standard error of sample means. So the famous word, that standard error, you have often come across in statistics, is the standard deviation of the sampling distribution of test statistic. So standard error is nothing but the standard deviation of the sampling distribution of the test statistic. That is very important. And what does standard error tell then? See, what does standard deviation tell us? Standard deviation, we have seen that it tells us about the spread in the data. So standard error is also a standard deviation. So standard error will tell us the spread in the data. Which kind of data? The data of test statistic. So how these values are varying? See, if you try to find out, in this case also, the range of the sample mean values are from 3 to 7, and the range of the data was from 2 to 8. So the spread in sample mean values is lesser than the spread in the data, and that leads us to an important theorem in statistics, that is known as the central limit theorem. If you feel that you are being bombarded by too many concepts and theorems, don't lose your heart. Just keep at the back of your mind that there is something called as central limit theorem, which makes the life of a statistician very easy. In short, one can say like that. Because using the central limit theorem, you can come to the normal distribution from any distribution. It's a very crude manner I am telling, but that is very important to understand. So let us read first of all what does this statement say. According to the central limit theorem, as the sample size n gets larger, the sample means tend to follow a normal probability distribution and tend to cluster around the true population mean. And this holds true regardless of the distribution of the population from which the sample was drawn. This statement is $1 million statement from the statistician's point of view. Your data might be coming from anything. It could be coming from gamma distribution, it could be coming from Weibull distribution, it could be coming from any discrete distribution like binary, Poisson, negative binomial. It could be anything, okay. You don't know the distribution, for example. But if you take the samples and the samples are large and you find out the sample means and you talk about the distribution of the sample means, the sampling distribution, now you know the word, the sampling distribution of the sample means, then those sample means follow normal distribution. So that is why normal distribution becomes a very central thing in statistics because of the central limit theorem. So from any distribution whatsoever, you can land, I would say, on normal distribution, and then you can use the normal distribution for all further inference, all further analysis likewise. So this we have actually covered. So this we are talking about the difference between the point estimate versus interval estimate. What is an interval estimate? I have not yet touched upon. So I will come to that. So using this central limit theorem and therefore the normal distribution, we can compute an interval. We can compute an interval. What is an interval? Interval is a piece of real line which is depicted by two numbers, say 5 to 10. So all numbers between 5 to 10 becomes that interval. So interval estimate is defined by two numbers between which a population parameter is said to lie. For example, A less than mu less than B is an interval estimate of the population mu. It indicates that the population mean is greater than A but less than B. See, all our attempts are directed towards understanding the population parameter and guessing the value of the population parameter in the theory of estimation. In point estimation, we want to pinpoint the value of the unknown population parameter. In interval estimation, we want to capture the value of the unknown parameter within an interval. So, an interval estimate provides a range of values for the unknown parameter on the basis of the sample. Now, why does one want it and what is the advantage of that? That we will think of later on. First of all, let us understand how to compute it. So, we require, in order to compute that interval, which is known as confidence interval, we require a confidence level. Now, what is a level? Level is the probability that the interval estimate will include the population parameter such as the mean, obviously the population mean. The things will be clear when we are trying to understand an example. For example, suppose we have computed the confidence interval and that is 95% confidence interval, and that confidence interval is for what? That is for the average height of an Indian. So my parameter mu is average height of an Indian, and I don't know this value. I don't know this value. I am trying to estimate it through interval estimation. I have come up with the interval 150 centimeter to 180 centimeter. And what is the confidence that I am having? I am having it, the confidence, as 95%. So the meaning of entire this statement, what is the statement? 95% confidence for the average height of an Indian is 150 centimeters to 180 centimeters. The meaning or interpretation of this statement is that the average height of an Indian will fall in the range 150 to 180 centimeters with 95% probability. So we provide you these two numbers as a statistician. We provide these two numbers with 95% guarantee that whatever is the height that falls within an interval 150 to 180 with 95% probability. For example, another better would be, let us again consider that sleep inducing drug, and the 90% confidence interval for the average increase in hours in sleep for a patient is say 2 to 7. What would it mean? That our drug will increase the sleep of a patient by at least by 2 hours, at most by 7 hours, and this statement we are making with 95% guarantee. So that is the interpretation of the confidence interval. What is the advantage? And why does one has to compute the interval estimation over the point estimation? See, point estimation, we give a value. We have a sample like that, average height 5 feet. So 5 feet was the sample value. That was an estimate of the population average mu. But we don't know what further we should talk about it. Either we can provide the standard error of that estimator to give an idea, but to a layman, it is better explained in the manner like this, that so and this is an interval with so and so guarantee, then it is better understandable for a common person. So that is why these confidence intervals are always provided, and they are not different from the point estimation. See, point estimation you have to do first, then only you will compute the confidence interval. How? Let us see. To calculate a confidence interval, we would need the confidence level, which is that 95% or 90%, that is known as confidence level, that describes the uncertainty associated with a sampling method. Rather than uncertainty, I would say the certainty associated with the sampling method. The statistic, the data that describes the characteristic about a sample. So you have to first compute that sample mean, that is a must, and then you will go here and there is exactly the words here and there. You will go here and there, or means on the left side and on the right side of that sample mean. So you will compute the range of values above and below the sample statistic, above and below the point estimator, and that will give you the confidence interval. So given these inputs, the range of the CI is defined by the sample statistic plus or minus margin of error. Four simple steps to construct a confidence interval. Identify a sample statistic like the sample mean, then select a confidence level. You decide which confidence level you would like to have. That depends upon the context very much. If you are very much into a kind of high profile drug like oncology patients you are trying, and then you are very serious about it, then you would like to have a very tight you must have 99% probability confidence, 99% confidence. So you will go with the higher confidence level. If you are talking about some such things like kind of ointment and whether it's effective or not and that, like that, okay, fine, so you can work with that 90%. So generally these values are decided beforehand in the protocol and by statisticians. Having decided them, you compute the margin of error. The margin of error is computed as critical value multiplied by standard deviation of statistic. Now you only will tell me that now don't call it as standard deviation of statistic, call it as standard error of statistic, and multiplied by critical value. Now what is this critical value? This critical value comes from the normal distribution, which is that z value. Okay. Specify the confidence interval like that the sample statistic plus or minus this margin of error which is computed here. So if you subtract that margin of error from sample statistic, you will get the lower limit of the confidence interval. When you add to it, you will get the upper limit. So when the margin of error is computed and you are subtracting and adding, that means what is the midpoint? Midpoint is nothing but the sample statistic, that is the point estimator. So point estimate plus here and there, as I said, is going to give you the confidence interval. Okay, actually one can talk lots and lots about confidence interval. It's very interesting topic. At the same time it is very thought provoking also, but I resist myself in doing that. Otherwise you will be bogged by this concept. Anyway, so from a sample of 32 patients on medicine shopping, the average order value is say $78.25. and the population standard deviation is $37.50. Let us calculate the 90% confidence interval for what? For the population mean, mu. Okay. Whatever you are having here, 78.25 is the sample mean. Here it is assumed that the population standard deviation is known and it is 37.5. That is why it is called as sigma. Sigma is known and you divide by root n, you get the value of the standard deviation or standard error of the sample mean. So here this is standard error of the sample mean. From that sample mean you add 1.64 multiplied by this standard error. Now where from this 1.64 is coming? This 1.64 is the z value which is coming from the normal probability tables, which is known as the critical value in the earlier slide. So you get this value and you go that much far away from the point estimate and you get the upper limit 89.12. Same thing you subtract and you get the lower limit 67.38. Now what statement will you make? That the average order value will lie between 67.38 and 89.12 with 90% probability. That's it. So that is an interpretation of the confidence interval. Okay, that's what is mentioned here. So interval estimate for the average value of a medicine. So this is the value here, you are going this much on this side, that much on that side. One can also compute one-sided confidence interval. Not necessary that you have to always go both ways. You can compute one-sided. You know that your drug is going to be effective. So you don't want to get the lower limit at all. You will say that, okay, tell us the upper limit, how far it can be effective or how much it can induce sleep if it is a sedative. You can talk about one-sided confidence interval also. So things become little complicated once we do that, but the concept remains the same. What is the meaning of this particular thing of 90% confidence interval? What does it mean? If we select 10 samples from our clinical bills population and construct 90% confidence interval around each of the sample means, then theoretically 9 of the 10 intervals will contain the true population mean, which remains unknown. So you are sampling again and again and again and again. You take 10 samples and from every sample you compute confidence interval. As your sample changes, sample mean changes, therefore the confidence interval changes. So you will get 10 different values of the confidence intervals. So by meaning the 90%, 9 of the 10 intervals, or I would say that if you compute 100 intervals, then 90 out of 100 intervals will definitely contain the value of the population parameter. Still it is unknown. It's not that you know the value, you are capturing, so you are trying to catch the value in your confidence interval. So here if you see, note that samples 1, this is the unknown population mean and these are the confidence intervals you are computed, and then the mean is going through all these 9 intervals, only one is aside and therefore that doesn't capture. So that's okay, that out of 10, 9 can capture the value of the. So that means if your sample is good, your confidence interval is bound to contain the unknown value of the population parameter. More than that, you don't have any other choice at your hand. Some such values of the Z statistic are provided here, which you can readily use. For example, if you want 90% confidence interval, then the value is 1.64, 95 1.96, 99 2.57. This is the standard error, sample mean, and then you get the confidence intervals here. If you observe these confidence intervals, see the first one is 67.38 to 89.12. Then 95% it has gone 65.26 to 91.24. That means it is travelled on this side as well as on this side. So, it has become wider. With 99% it has become further wider. So, as the confidence level increases, the confidence interval will be wider and wider and wider. Okay. Because then you don't want to err, on your estimation. That is why you have to be very cautious. So, what will be 100% confidence interval? 100% confidence interval theoretically will be the entire real line. So, you will say that the average height can be any number. I can tell you with 100% guarantee that the average Indian height can be any number on real line. Okay, so jokes apart. So, that is why people generally stop at 99%. But still, with some critical situations, you can talk about 99.95% confidence intervals, etc. Okay, so note that when we increase the CI, our interval estimate of the true population mean becomes wider and less precise. So, what have we learnt today? What is the subject of statistical inference? The distinction between parameter and statistic. When we use a statistic to estimate the parameter, we call it as an estimator. So, estimators of parameters, population and sample, point estimate, basics of interval estimation, point estimate versus interval estimate. In between we saw the gist of central limit theorem also, interval estimation, confidence interval, data requirements and construction and an example. These confidence intervals today we have come up by using the Z statistic, which is nothing but the normal distribution based test statistic. Instead, if you are in the small sample setup, then you can use T test also, T test, F test. So, it's not that for computing the confidence interval you have to always choose normal distribution, no. If you want to be more precise and if you know the proper model, you have smaller data, then you can go in for computing the exact confidence intervals without considering the normality due to the central limit theorem and all that. The topics are more and more involved. We will not touch them here, I suppose.